So.
Okay, I'm back. Yeah, actually the issue was also on my end. So apparently I didn't give my computer permissions to share my screen. So, but my Zoom has permissions now. I'm ready.
Awesome.
Cool, thank you. So can everybody see if I go, yeah, I'm going full screen now. Is that still working?
Yep, looks good.
Okay, perfect. Thank you. Okay, so we're gonna get started. Hi everyone, my name is Pemmaraju. I'm a Qiskit advocate and quantum ambassador, currently at IBM. And I will be talking to bit today about Qiskit Nature and Optimization, sort of at a pretty much at a high level. So I'll try to motivate the different types of problems that we will encounter and solve within the two different packages. But since we have a 1 hour, I wanted to keep this mostly high level, but sort of leverage the commonalities between the two packages to sort of provide a common theme that you can use across both packages, actually. So with that, let me get started. Back, quantum computing goes back to the 1980s, early 1980s. When Feynman observed that in order to solve problems that arise in the physical sciences, in fact, classical computing may not be good enough, and in fact, we might want to think about creating quantum mechanical devices that could actually simulate other quantum systems, namely nature, perhaps more efficiently. And today, indeed, there isn't a lack of problems both in the natural sciences and physical sciences, as well as some other domains like the social sciences that are sufficiently complicated. For instance, we want to improve agriculture by creating better processes for nitrogen fixation. We want to, in order to mitigate climate change and become more energy efficient, we want to create better catalysis, including, for instance, carbon capture, or to make better hydrocarbons to both make CO2 as well as split water and so on and so forth. We want oops, sorry. The video is blocking my screen. Okay. So yeah, we also want to be able to deal with problems in the social sciences, like in the case of finance, for instance, to improve the predictability and the stability of financial markets. And as we all have seen more recently, we want to be able to create new classes of antibiotics, antivirals, and so on to manage the risk of healthcare risks across the board. So it is. Today we understand that in many of these domains, there are several classes of problems that are intractable if you look at them from a classical computing perspective, and that is where sort of quantum computing comes in. And today's talk, Qiskit Nature, Qiskit Optimization, sort of touches many problems in these across these different fields. So let me introduce Qiskit Nature and Optimization very quickly. Qiskit Nature is an open source framework for solving natural science problems using quantum computers. And then Qiskit Optimization is an open source framework for high-level modeling of optimization problems, and also provides easy-to-use quantum optimization algorithms that you can also adapt for various other tasks. So if you look at the target applications that are currently supported, on Qiskit Nature, we have molecular chemistry, which involves electronic structure and vibrational structure. In the biosciences, we have protein folding. For physics and material science more broadly, we also have lattice models that are supported. On the Qiskit optimization side, currently a lot of combinatorial optimization problems are supported, and it is very easy to code solutions to several problems in these class, like graph coloring, job scheduling, traveling salesman problem, and so on and so forth. So today we will explore the common theme that I want to explore today that sort of connects these two different modules is that of variational approaches. So we will explore the variational approach and how we can use that to solve problems across both these domains using a very common recipe, if you will. So with that, let me sort of present the general recipe that we will go through today to approach these problems both within Qiskit optimization and Qiskit Nature. Because the audience is more general, I'm told there's a mix of students across computer science and other domains, and not just from physics and chemistry. So what I will do is I will start with Qiskit optimization, and then I will move to Qiskit Nature towards the second half of the talk. And Qiskit optimization, we will use Qiskit optimization to set up the overall framework, and then we will specialize it to Qiskit Nature. So this is the general recipe that we will go through today in order to solve an example problem on the optimization side, and then also another problem on the electronic structure side. So this is, as I've written it down here, roughly consists of 6 steps. And we will see why I have split it up into these 6 steps as we go along. So the first step is to sort of map your problem onto an appropriate cost function or Hamiltonian. I will indicate Hamiltonians by the letter H, and this particular Hamiltonian, this notation indicates that W is a set of parameters that characterize the Hamiltonian, and this vector X is a set of inputs that the Hamiltonian takes. So given an input X, the Hamiltonian will evaluate to a scalar, but the Hamiltonian itself is parameterized by this weight vector W. And then the second step is to typically to compute the parameters of W that would then specify an instance of your problem Hamiltonian, right? So, and you might have to use classical computing to do that, sometimes if needed. And then the third step in the process, because we want to use quantum computers to solve these, is to then map the parameterized classical Hamiltonian that we have prepared onto a qubit Hamiltonian. And we will discuss this transformation process in the case of both the max cut problem on the optimization side, as well as the electronic structure problem with Qiskit Nature. And then the next step, the fourth step, is to identify a suitable variational ansatz. Remember, we are going to be discussing variational methods today. So, and central to that is this notion of a variational ansatz, which is basically a parameterized quantum state, defined such that the parameters that specify the state are classical, and these are to be optimized. And then the target for the optimization is the expectation value of the qubit Hamiltonian that we define up here. So by minimizing the Hamiltonian expectation in the ansatz space defined by this variational ansatz, we will obtain a solution to our problem. But in order to do that, step 5 is to identify a suitable optimization scheme. In our case, it'll turn out to be VQE, which is a hybrid quantum classical optimization scheme, which we will discuss. And then at the end, the final step is, once you have the solution, on the quantum computer, there might be some sort of post-processing that is needed to translate the result into a form suitable for consumption. And then the main idea here is that Qiskit provides tools for us to do each of these steps, with very, very conveniently, thus making it very easy to solve these problems. We will consider in this talk quadratic optimization as well as electronic structure, both of which will sort of follow this general recipe. By the way, if anybody has questions, feel free to stop me, and then and I'm happy to explain along the way. Okay, so let's start off with Qiskit optimization. I will be following closely the tutorials that are already on Qiskit optimization tutorials. So this one, for instance, is from the Qiskit tutorial on quadratic programs. So yeah, please look for these links at the top of my slides. And the idea here is that once this talk is finished, maybe you might want to visit those actual pages and follow the hands-on sections that are given in those tutorials, so that you'll be able to see what we discussed today actually in practice, within a Jupyter notebook that you would create and maybe save for later use as well. So okay, so with that, so let's so Qiskit implements optimization problems within this general framework called quadratic programs, which are a generic representation for optimization problems. And they're defined as follows. Typically, you are asked to minimize a quadratic form of this type, subject to certain inequality constraints specified by matrices A, vectors B, and then also individual constraints on the individual bounds on the variables. Okay, and then so you can look at the definition of these different quantities that enter these definitions. So where Qi are n by n matrices, A is an m by n matrix, X and C are vectors, and remember X are variables here, and everything else is sort of specified, our parameters specify the problem. And then, so the idea here is that this is a very general setting, but we have gadgets to always convert a problem that is framed in this general setting into what is known as a quadratic unconstrained binary optimization or a QUBO problem. Therefore, we only need to consider, for our purposes, the specific type of quadratic optimization problem, which is a QUBO. Qiskit provides a general class called quadratic program to QUBO, which is a wrapper to convert any generic quadratic program or those that can be converted to QUBOs into QUBOs. So, so of course the main feature, the appealing features of QUBOs are that QUBOs feature binary variables, namely the x's that appear in the problem can only take on values that belong to bit strings, so n-length bit strings in this case, and they do not feature, and QUBOs do not feature explicit constraints. So any constraints you have in the original problem would have been converted into penalty terms in the cost function of the QUBO. And then the other nice feature QUBOs have, which is especially convenient for quantum computing, is that QUBOs can be mapped to Ising Hamiltonians. So everybody who's probably from a computer science background already knows about Andrew Lucas's paper on converting all kinds of NP problems into Ising Hamiltonians. But if not, I highly recommend those of you who are interested in using Qiskit optimization to really go through this paper, because it is a useful exercise. Okay, so with that, so we'll now go through sort of a concrete example of a QUBO problem, namely weighted max cut. This is also a tutorial that is available on the Qiskit web pages, and it's formulated as follows. So, given an n-node undirected graph, specified as a collection of vertices and edges, where you have n vertices, and you have positive edge weights, wij, such that they're also symmetric, wij equals wji for each edge, ij. The task is to partition the original set into two disjoint subsets, such that the sum of the weights of edges connecting points in the two different subsets is maximized. So now this sounds like a mouthful. So let's actually take a look at an example to see what we mean. So given this sort of 4-node graph, the task is to find two partitions of the graph such that following the max cut operation, you have two subsets. So in this case, the red nodes and the blue nodes. And if you count up all those edges that connect the red nodes to the blue nodes and vice versa, that sum should be maximized with respect to other ways in which you could have partitioned the same graph. So in this instance, we see that the cut is defined by this blue region that I've drawn. You can either think of the cut as isolating the two blue nodes, or as encompassing the two blue nodes or excluding the two red nodes. And if you sum up the weights on the edges that cross the cut, right? So you have 4 edges that cross this particular cut. So 1, 2, 3, and 4. And so the total weight of these edges is 4. Whereas, for instance, if you had drawn the cut a bit differently, for instance, if you had cut it, let's sort of right through the middle here, it's easy to see that you would only have 3 edges crossing the cut, right? So the idea is to always find all, explore all the different ways in which you can partition the graph, and then find the particular partitioning which maximizes the weighted sum of the edges that cross the cut, right? So in this example, we see the maximum such weight is actually 4. Now, so the step 1 in this problem is to actually map this onto an approximate cost function, or equivalently a Hamiltonian. Now, for max cut, we in fact will start from the opposite of a cost function, which is a profit function, which is to maximize, because this is a max cut problem, right? We want to maximize something, namely, we want to maximize this profit function here, where Wij are the edge weights, and we will actually consider this in a slightly more general setting where we also add this extra linear term. Although for the simple max cut problem that we're going to solve, these linear the weights in the linear term will be 0, but it's useful to take note of the fact that the methodology that we will develop actually applies to this slightly more general setting. So we have again, xi are binary variables which can take a value of 0 or 1, and we assign such a value to each of the nodes, namely if nodes that are 0, say, it can be blue, and nodes that are 1 will be red, and so on and so forth, such that nodes with the same value are in the same partition, right? And this cost function clearly satisfies the criteria that we want. For instance, it's easy to see that Wij contributes to the sum only if xi equals 1 and xj equals 0, right? But only then this product is not 0, namely, and then in that case, edge ij crosses the cut, and so that appears in the sum. If xij contributes, then if Wij contributes, then Wj does not, because if xi is 1, xj is 0, Wji will contribute only in the case where xj is xj is 1 and xi is 0. So this is also what we want, because in this case, each edge contributes at most once. So these two conditions sort of satisfy the conditions for max cut. And now the effect of the linear term can also be understood very easily. It's clear that let's consider a more simple graph where we only have 2 nodes, and we have these linear weights W1, W2, and then the edge weight W12. It is clear that if you consider non-negative W1 equals W2, and each of which is less than W12, in that case, the optimum profit function will be obtained either when x1 equals 0, x2 equals 1, namely the 2 nodes are in opposite partitions. But if non-negative W1, W2 are greater than W12, it is more profitable actually to ignore the edge weight and just keep both nodes in the same partition, right? So depending on the interplay between the linear and the quadratic term, the whether or not you decide to partition the graph one way or the other will be affected non-trivially. So there, therefore, it might be useful in some real world settings to actually have this this linear bias term in your profit function. In the simple max cut problem, we don't need that, so we're going to set these wi's to 0 moving forward, and we'll only work with this quadratic term involving the couplings wij. Okay, so step 1, so we have a profit function, and then step 2 is to compute the parameters of the function, because we want to adapt the general form specified by this c of x to a specific instance, right? So in the simple instance that we considered here, all the wij's are 1. It's an equally weighted graph. But in other instances, you might want to consider a different set of weights. But in most real life, the weights are typically given to you, at least on the optimization side, by some sort of domain expert. So this may not be the case in other settings, but in these settings, we can assume safely that is the case. So there's not much that we need to do for step 2, which brings us to step 3, namely to map the parameterized Hamiltonian to a qubit Hamiltonian. But remember that we so far only have the profit function, right, c of x. So we're now going to directly convert this profit function into a corresponding qubit Hamiltonian. So for that, we need to remember that QUBO problems have this nice feature, namely that they can be mapped to an Ising Hamiltonian, right? So each of the variables xi in the QUBO problem, which is a binary variable, can be mapped to this operator 1 minus zi over 2, where zi is a Pauli Z acting on 1 qubit on a quantum device. So Z has a matrix representation shown here in a 2-dimensional Hilbert space that defines the qubit. It also has sort of a Dirac operator representation shown here. When Z acts on a qubit in state 0, it returns a 1, 1 times the same state. If Z acts on a qubit in the other state, namely state 1, indicated in this Dirac notation, it returns -1 times the same state, which in turn means that if you calculate the expectation values of this operator, actually the one here should be interpreted as an identity, 2 by 2 identity matrix. So if you compute the expectation, we see that in state 0 we get 0, and in state 1 we get 1, which is exactly what we want, because the xi's are binary variables. They should either take a value 0 or 1. And through this mapping, what we're saying is that the expectation values we would realize by using this operator either in state 0 or state 1 correspond to the values, the xi values, the classical xi values that we want for the classical problem. So given that that is the case, we can go ahead and substitute this expression 1 minus zi over 2 into the profit function we wrote down earlier, and that just starts looking like this. After some very minor algebra, we will end up with this function here in these large parentheses plus a constant. And because the constant doesn't really matter for maximization or minimization, and because the coefficient in front of these brackets is negative, we can say that maximizing the profit function is equivalent to minimizing this Hamiltonian, which is the term, which is the sum of the terms inside these brackets here. So And the nice thing about, and then since these the operators that appear here inside this Hamiltonian are these Pauli Z operators or quadratic products of them, and so this is a form of Hamiltonian that can be easily evaluated in the computational basis on a quantum computer, and the desired solution is usually one of the basis states that minimizes H. We will see what that means in a second. But the difficulty that we will encounter is that there are in principle 2 to the n basis states to search through in order to find the optimal configuration. Okay, so before we sort of expand more on that, we should consider the idea of solving this problem by brute force. Okay, so if you wanted to solve this purely classically by brute force, let's say we did not have access to a quantum computer, and while there are many clever methods of approaching max cut, using heuristic classical schemes, we're just going to consider the brute force approach, namely, what we have to do is sort of enumerate each of the possible configurations that this graph can take, namely, because we have 4 nodes and each node is a binary a variable. It can each of these nodes can be assigned as 0 or 1, which means we have sort of 16 classical configurations that are possible for this 4-node graph, and for each of those configurations we can plug that configuration into our profit function and just calculate what its value is. And if we do that procedure, we will see that the best solution is the 1 0 1 0, namely 1 0 1 0, where the blue nodes are ones and the red nodes are zeros, for instance. Equivalently, there's another by symmetry there's another configuration 0 1 0 1 in this case, which also gives the same energy, but we just need either one. We're just going to go with 1 0 1 0, right, as a solution. So that is the valid solution. But in order to find that, in principle we have to just plug in every possible bit string and then just evaluate its profit, right? Now we could do something similar on a quantum computer, right? We could naively just map each of these classical configurations onto a classical configuration of a 4-qubit register. So if I have 4 qubits, remember each qubit, the classical basis available to each qubit is either 0 or 1. So the computational basis that one has on a quantum computer is completely specified by these 16 configurations of the 4-qubit register. So bit strings going from 0 0 0 0 to all the way to 1 1 1 1. And you could we already saw in the previous slide that just as we could plug in these classical values for xi xj into the profit function, we can equally well construct these qubit registers and then evaluate their expectation values in this Hamiltonian now, and we will basically get the same result, namely that the 1 0 1 0 configuration will give us the lowest minimum value for the Hamiltonian, and in turn the maximum value for the profit function. But again, if we were to do this way, right, we would be scanning through all to the n configurations, but and so that's something we want to avoid, right? So now next we'll discuss how we would actually approach this now on a quantum computer. So the idea here is instead to take advantage of the fact that on the quantum computer we can represent a generic superposition of all the basis states at once. Namely, instead of having to consider each of the basis states individually, so I'm going to show here, again, enumerate all of the different basis states that we have for this 4-qubit problem, and then I'm going to call them B0 to B15. A generic state that we can prepare on the quantum computer is instead a linear combination, written here in Dirac notation. It's basically a sum over each of these basis vectors times some coefficient. Namely, this is a linear combination of these basis states, right? So on a quantum computer, we have access to a vector space structure, which we do not have on classical computers. And so the main point of trying to with these variational approaches is to see if we can take advantage of this to find a way that is better at approaching this desired solution than the brute force approach that we saw before. So typically, right, the state size specifies a distribution of probability amplitudes across the basis states. So if I assign, for instance, an equal value of 0.25, so to each of the CMs here, I'm going to get this sort of equal superposition state across all 16 computational basis states. And in this simple problem, we already know the result we want. So for the idea is that if we, following an optimization step, we want to end up in a state instead that has its probability amplitudes distributed in this other form, where there's the basis state 1, 0, 1, 0 is dominating the amplitude, whereas all other basis states have a corresponding amplitude that's either tiny or 0 altogether, right? So this is where we don't necessarily have to start here, but if you have no prior knowledge about where to start, you might as well start from an equal superposition state, and then following the optimization procedure, you want to end up here, right? So that is what we want to do, and in order to do that, we move to step 4, which is to identify a suitable variational ansatz indicated here by psi of theta, and this has to satisfy two properties, right? The ansatz is to be specified by a set of classical parameters, which are going to be need to be optimized. And the optimization target is the expectation value of the qubit Hamiltonian that we prepared earlier, taken with respect to the ansatz state, right? And typically in Qiskit, the type of ansatz that is recommended for problems of this type, namely Kubo problems, is of this form. So you start with the plus here indicates a shorthand for an equal superposition state, and then you apply a series of entangling and single qubit rotation gates in succession. So a circuit diagram for something like that looks like the following. So you start with your 4 qubits in the 0 state, and then you apply rotation gates to get it into this equal superposition state. Or it could even be Hadamard's, for instance. And then you apply the entangling gate. In this example, is a controlled phase gate. So, so shown here by this in blue. And so you have basically in this diagram we have 5 layers of these. So we have an entangling gate followed by single qubit unitary applied here, and another entangle gate and unitary, and so on and so forth. So each of these is and there's 5 iterations of these happening. So 1, 2, 3, 4, 5, right? And so at the end of this, so the hope is that every time you add an extra layer by increasing this exponent m in this expression, you are adding extra parameters to your ansatz. So in this example, we have about 24 parameters indicated here by theta, right? And so once we have this ansatz state, we can evaluate, we can assign different values to the classical parameters theta, and for each assignment, we are then able to evaluate the expectation value c of theta of the Hamiltonian, like so. So we split up the Hamiltonian into the individual terms, and for each term, we are able to evaluate the expectation value, and then we sum up all the terms at the end. Okay, so that is the general process. And which brings us to step 5, which is, try to identify a way of sort of, automating this process to get you from an initial starting guess for your parameters theta to the optimal parameters that will define the solution state, right? And for this, the most popular approach right now is the variational quantum eigensolver, which was introduced in this paper in 2014. And this has the following general structure. You prepare the state, meaning, going back to the previous slide, once you've chosen the ansatz, preparing the state means just assigning a set of values to your parameters theta. Once you do that, you pass the same state to one of n quantum modules, each of which, the purpose of each of which is to evaluate one of the terms that defines your Hamiltonian. So in our case, right, our Hamiltonian is written as a sum of several terms, a number of these linear terms, which are 0 in our case, but in the general case they would exist, and some of each of these quadratic terms which feature these sort of products of Pauli Z's, right? So you'd have to evaluate the expectation for each of these terms separately. That is what this diagram indicates. Now, sometimes you're able to group, different products, different strings, and sort of calculate the expectation values together. And there's a lot of technology behind that. But in the general case, you have to split up your Hamiltonian into all the individual terms in it, and you just calculate the expectation value for each term, and then use a classical addition to just add up the expectations. Okay, and that basically gives you the final, the full expectation, which you then pass to the classical optimization routine. So you made a guess, and then you evaluated the value of the Hamiltonian for that particular guess, and then the classical optimizer will then decide how to update your guess for the theta parameters, so that you have a new trial, you have a new set of thetas, which you go through the whole process again, preparing the state, evaluating the expectation value, and you keep doing this until the value of the Hamiltonian is minimized, right? So this is sort of the variational procedure, if you will, that is at the heart of all these optimization problems. And in terms of sort of like the choice of the classical optimizer you might want to use, the Qiskit textbook recommends two different ones for different scenarios. If you're actually working on either noisy simulators or on real hardware that is always susceptible to noise, the simultaneous perturbation stochastic approximation optimizer, SPSA, which is available to you as a module that you can just call, is recommended. If you are working in a noise-free setting, then they recommend Kobila, which is a gradient-free optimization scheme that converges very nicely for most simple problems. So, and then which brings us to the final step. So, we assume that, having gone through the VQE process, we actually have an optimum. And then, in this case, remember that the optimum that we will get will be represented again as a superposition state across the computational basis state, computational basis states for the specific problem. But we actually want as a result a classical configuration. So what we're going to do is we're going to take this state and we're going to sample it. And because it may turn out that the amplitudes on those configurations that are not the solution we seek are small, but they're not necessarily zero. So when you sample, it's the most likely result is going to be the configuration that we desire, but there's also some small probability that you will get the other configurations as well. So you should therefore use sort of you should sample sufficiently a sufficient number of times to make sure that you are able to identify the most likely configuration that your state actually encodes, and that is implemented in a sort of a sample most likely function provided by Qiskit. So you pass your resulting eigenstate, again, which is a superposition over the computational basis states into the sample most likely function, and the result will be a classical bit string that you can which represents your result, and you can plug this into your original profit function to get at the final result for the problem. So that is it for MaxCut, and the thing that is remarkable about Qiskit optimization is that each of the different steps 1 through 6 that we discussed so far roughly translates to about 1 to 2 lines of Python code, and you can solve optimization problems of the type that we've discussed here using roughly about 10 lines of Python code or less. And to see that for yourself, I would again recommend that you go to this tutorial 6 on MaxCut and Traveling Salesman, and then work through the Jupyter notebooks there. Hopefully this this discussion, it will be helpful as you work through those notebooks. So next I will move on. Let me see how much time I have. Okay, I have about 10 minutes, but I think we should be, I can go much faster here. So the next thing is Qiskit Nature. And remember, so for Qiskit Nature, the advantage we have is that the step 1 is kind of already done for you, in the sense that problems in nature arise out of either classical or quantum mechanics, and therefore are naturally described by known Hamiltonians. For instance, in the electronic structure case, which is one of the main modules in Qiskit Nature, we are dealing with the detailed von Oppenheimer electronic Hamiltonian, which I will introduce on the next slide. For vibrational structure, there's the so-called vibrational Watson Hamiltonian. And then for protein folding, there's the coarse-grained protein folding Hamiltonian. And then for lattice models, the idea is that you're going to define your own Hamiltonian. So it's a lattice models is a more general framework, but on a so-called lattice graph. And I've identified which of these Hamiltonians are quantum and which of these are classical. So electronic vibrational lattice models are meant to be quantum Hamiltonians, meaning that they deal intrinsically with quantized degrees of freedom, whereas protein folding is very similar to the sort of optimization problem, classical optimization problem that we discussed until now. So with that, let me sort of explain a little bit more about the difference between quantum versus classical problems. So we already saw that solutions to problems described by classical problems, such as the MaxCut or other optimization problems, generally correspond to a classical configuration that we may identify. In our case, it was the classical bit string 1010. But the solutions to quantum Hamiltonians are qualitatively different. A solution state to a typical quantum problem is typically an entangled superposition, namely it cannot be reduced to any classical configuration in any basis that you might choose. So I'm showing, for instance, some generic state in the computational basis, but it doesn't matter. No matter which basis you might want to adapt, there's no way in which you can sort of reduce this state into a distribution of probability amplitudes that would make sense as a classical configuration. But nevertheless, the recipe that we have laid out previously for the optimization problem works pretty well, even in this case. And the reason for that is because electronics structure, vibrational structure, protein folding, all these problems are also defined as optimization problems. So for the electronic structure problem, we have the full quantum chemical Hamiltonian written here. I will not go into details on this in the interest of time, but if anybody has questions, I will be able to go more in depth. But we're going to for the electronic structure case, as implemented in Qiskit, we will be working on the so-called Born-Haber Hamiltonian, which is derived from the original Hamiltonian through the so-called Born-Oppenheimer approximation. Okay, so and then we can give sort of a hand-wavy explanation picture that is associated with this Born-Oppenheimer Hamiltonian, which is that molecules are like graphs where the nuclei are the vertices. Here I'm showing a caffeine molecule where you have sort of nitrogen, carbon, and oxygen atoms, and also hydrogen, which are not marked as the vertices of this graph. But electrons are quantum degrees of freedom that live in a potential that this graph defines, but the electrons themselves are not assumed to be confined to any particular edge or vertex. And so the potential that the graph defines enters in the second term here in the electronic Hamiltonian, where the nuclear coordinates are defined by these capital R's, and then the lowercase r's are supposed to be the coordinates of the electrons. But like I said, they're not to be associated with any particular node or vertex, node or edge. Now for applications in chemistry, the ground state energy, which is defined as the expectation value of this electronic Hamiltonian in the so-called ground state, is a key property. And the ground state has the feature that it is the minimum energy eigenstate of the Hamiltonian. That is, it minimizes the expectation value of the Hamiltonian in the space of all possible states that the electrons can take. Now, it's obvious from this definition that, again, this is an optimization problem involving quantum degrees of freedom in this case, as opposed to classical degrees of freedom. But the overall optimization procedure we laid out previously applies equally well. Now, while step one is easy, step two, namely computing the parameters of the Hamiltonian you actually eventually want to map to the qubit Hamiltonian is actually much more involved in the case of the electronic structure problem, as opposed to max cut, as we saw before. So the actual Hamiltonian that I showed in the previous page is something known as the first quantized Hamiltonian, written in first quantization. And what you actually do is you have to solve a simpler problem known as the Hartree-Fock problem in this language of first quantization, which will then allow you to compute the so-called one-body and two-body integrals. And these integrals are calculated using these single particle orbitals phi that you obtain from the Hartree-Fock calculation. And then once you've calculated these integrals HQP, HPQRS, these in turn out to be the weight matrices that enter what is known as the second quantized Hamiltonian. Okay, this whole process is very specialized. Typically, this requires several lectures in grad school or upper undergrad courses to sort of get through this whole procedure. But I want to make it simple and just say that the point of this exercise is to yield a setup where each element of the computational basis, right, which we already saw, represents an anti-symmetrized product of Hartree-Fock spin orbitals, otherwise known as a Slater determinant. And the good thing about Qiskit Nature is that it sort of automates this entire process for you. So even if you've never done, first and second quantization explicitly in your own studies, that's not going to stop you from being able to solve molecular electronic structure with Qiskit, because this whole thing again is automated for you with the help of driver routines that Qiskit provides out of the box. So now the step three is again to map the electronic structure problem, the second quantized Hamiltonian that we saw here, which features these so-called creation and annihilation operators onto corresponding qubit operators, which are typically Pauli operators that we want, right, that we can easily deal with. And then this process is given by this so-called Jordan-Wigner mapping, where and the mapping here in the most simple terms that I can explain is every spin orbital that you get at the end of your Hartree-Fock calculation maps to 1 qubit. So in this particular cartoon here, we have 1, 2, 3, 4, 5, 6, 7 times 2, 14 spin orbitals. And then that will actually map to a 14 qubit problem, where each of these sort of circles and arrows represents a qubit. So I will not go into the details again of the Jordan-Wigner transformation, because this requires several lectures to sort of cover on its own. But the idea is that you start off with a second quantized Hamiltonian, which, remember, Qiskit makes it easy for you to calculate. You don't have to do any of these computations yourself. So you get a second quantized Hamiltonian form here, and then you call another function which simply applies the Jordan-Wigner transformation to a Hamiltonian written like this to get you a new Hamiltonian, which is mapped to the qubit Hamiltonian, which you will recognize by the fact that the terms in the Hamiltonian are all products of Pauli operators Z, X, and Y. Okay. So while these strings look rather long and cumbersome, you never have to actually do any of these calculations yourself. All of this is automated. I'm just showing here the end result, just so we get an idea of what's going on. And then, which brings us to step 4, which is just as we did in the case of the max cut problem, we want to identify a suitable variational ansatz parameterized by a set of parameters theta. And then we want to minimize the expectation of the Hamiltonian, in this case, the electronic Hamiltonian in the ansatz space. And for this, there's a popular ansatz. I mean, there are several, but the most popular ansatz, I would say, in chemistry at the moment is the unitary couple cluster and other variations on top of this one. And this, again, this ansatz starts off by acting this exponential operator, exponent t minus t dagger, onto a Hartree-Fock state. Remember, the Hartree-Fock states correspond to the basis states, computational basis states in our problem via the first to second quantization exercise that we performed earlier. And each of these t operators is actually a sum of several other individual operators composed of these products of creation and annihilation operators. Again, this is a lot of detail that you will learn if you actually do quantum chemistry. But for this general audience, I will skip over the details and only note that going through this whole process will again yield a nice unitary which involves products of exponentials featuring the parameters of the problem. So if I've switched notation from theta to t in this case, so the parameters now are these tj's, and then products of Pauli operators. So a typical circuit might look something like this. You see, you have these exponential operators involving strings xy, x, z, zy, and so on, applied one after the other, which is a result of trotterizing the UCC ansatz and mapping it onto a quantum computer. So again, the idea is that at the end of this process, you have these classical parameters t here that completely specify your state, because everything else that appears, such as these Pauli products, are fixed. The only thing that you can change are these classical parameters t, and by assigning different values to these classical parameters, you are exploring different states in Hilbert space. And so step 5 and 6 is again exactly the same as we saw before for the max cut problem. Now that we have set up a classical ansatz, we're going to again apply VQE. Namely, we're going to prepare the initial state, measure the expectation values, in this case of the Pauli products, into which the Hamiltonian has been split up, and then by collecting, by summing over all these and collecting them into the energy expression, we can pass that to our classical optimization routine, which will then adjust the parameters, send it back to our quantum computer, and we just iterate until we get our minimum energy. And then step 6 in the quantum chemistry case actually involves computing. Once you have the ground state energy and the ground state wave function, again specified by the optimal set of parameters theta star, for instance, you can then compute expectations of other observables of interest, such as dipole moments, and so on. And all of this is again made very easy by the so-called property framework of Qiskit Nature. So I would recommend those of you that actually do solve for instance, the hydrogen molecule problem or the lithium hydrogen problem, to then check out the property framework to compute some of the other properties that basically come for free once you've actually solved for the ground state. So with that, let me stop and then thank everybody in the audience for the attention. I may have gone over time. Let me see. Okay, 3 minutes over again. That's fine. Okay, thank you.
Thank you, Das, for the very informative talk. I know how difficult it is to fit 2 different topics into a 1-hour talk. So any questions from the audience? Maybe I'll start with one. So you briefly mentioned that you have you talked about 2 different optimizers, the SPSA and the other one is Cobila. Yeah, so I was just wondering, why is Cobila more suitable for noiseless simulations?
Well, so because the Cobila is a sort of a gradient-free approach, and the idea is that if you're actually calculating gradients, and so the not just gradients, actually, even the expectation values that we're calculating are not exact, right? So the effect of noise is to sort of make the expectation values that you compute, inaccurate, right? So how do you the idea is then, okay, how do you work in a setting where the results you have are not the exact ones that you think you're calculating, right? And then the SPSA is specially designed to sort of use probabilistic technique to sort of mitigate the fact that you have noise in your in the setting, whereas Cobila doesn't have any such mitigation techniques. I mean, it just Cobila thinks that what you give it is the truth, is the ground truth, and so if it turns out that the expectation values you were computing are only approximate and every time you run this you get a slightly different result, right? So Cobila does not work very well in that setting, because the assumptions underlying Cobila are that the function evaluations that you are giving it are the exact values of the function, not some noisy approximation to the function.
Great, thanks. Any more questions? People on Zoom, if you have a question, you can unmute yourself. Well, I guess not. So Das, thank you again.
Thank you. Thank you, everyone. Thank you, Rihal. Thank you all for the opportunity, and good luck with the rest of your Fall Fest, right?
Yeah.
All right.